Welcome to Software Engineering. This is lecture number 10, Software Testing. Today we're going to talk about the motivation, why we want to do testing, what are some of the guiding principles, what are the different levels of testing, the test writing process, how we write the process, how we write the tests, and what is a software tester and the different types of tests. Okay. Um, Importance of software testing is immeasurable. Software failures can cause discomfort, even financial loss, even harm to people and death. And here are some examples. A airline crash in 1994 was due to a software bug. Um, in 85, there was extra radiation given to somebody because these radiation machines are controlled by computers. In 1999, there was a bug that caused the launch of a military satellite to fail. This cost over $1 billion. Um, there was another software bug in '96 from that caused bank problems. He credited the accounts of 823 people with $920 million. That's what might have been nice for them. Another example. There are more examples. History is full of other examples. So we obviously don't want bugs. Bugs. Recently, the Boeing 300 Max, part of the reason that they crashed is because of software bugs. So the understanding today is that software testing helps prevent such crises, reduce the risk of using faulty software. The earlier testers will discover the faults in the development process, the less embarrassing the faults will be, and the less damage they'll do in the real world, and the easier it will be to fix them. So what is software testing? It's part of the project life cycle where to identify whether the software meets the following criteria. Is it correct? Is it complete? Does it do, not only is it correct, but does it do everything it's supposed to do? And is it quality? Is it, does it work well? I guess, is it slow? Is it hard to use? So software testing is an activity that verifies that the software system, it has no defects. It should be done before the user finds them. So here's a definition. Software testing is a process which includes many different activities. Testing the end results is only one of these activities. The test process also includes activities such as test planning, as planning what tests you're going to do, analyzing and designing and implementing the test, and then reporting test progress, results, and evaluating the quality of a test object, and evaluating the quality of the tests themselves. So an application has many components. Okay. And each of those components has units. What are these units exactly? Every programming language has its own unit. For example, if you work in Java, then each unit will be a class. A class could be a unit. As you can test, does this class work? If working in JavaScript, then each unit will be functions or modules. The truth is, the definition of a unit could be different even within a particular language, but it could be a function, basically, or it could be a class. It's the smallest unit. The other components interact with each other. Okay. Well, there's the components. The components are composed of units, and they interact with each other. So there's four, I guess, different levels of testing or different types of tests. And they are in stages. The first stage is the unit test. Each component, which is that small part, is tested by itself. Does it do what it's supposed to do? This is usually done by the programmer himself because he's using that unit. But it could also be done by a testing team. Integration test. The integration among the components is tested. In other words, each component maybe works, but do they work together? If you see, we kind of skipped something here, which is component testing. And I think that's because unit testing could be understood to include component testing. We test the units, and then we test the whole component. But we didn't yet test how the components interact with each other, and that's integration testing. It also tests between the system and outside systems, because our system may interface with another system, or between other people who use the system. System tests. Does the entire system do what it was intended to do, and how well does it do it? So now we test, okay, the parts work together, but does the system achieve our overall goals? And then there's acceptance testing. Did we create the correct system? Does it fulfill the actual requirements? It's very similar to system testing. But the first one, system testing, is does it work the way we intended it? And acceptance testing is, does the user, does the person who ordered this, who requested this software, agree that he accepted? Does it do what he wants, or she? Or if there's just a defined requirements, then does it fulfill those requirements? Static testing. So now there's two different kinds of testing. This is all dynamic testing. If you notice, the title here is dynamic testing. But now we've mentioned here static testing. So what is static testing? It's simply to test that the software runs. So static testing is like the most basic level, that it does it actually run. We forget whether it does what it's supposed to do, but does it run at all? If it runs, but it doesn't do what it's supposed to do, well, that's a different story, right? So we're just testing that it's running is static testing. So unit testing again. Unit tests are the lowest level. So what are you checking? A unit can mean a class, like we said. Each component of the application is made up of several classes. Okay. Purpose of the test. Check that the unit does not contain bugs. If there are no defects, then it is said that there are no bugs in the software. Unit testing. Under unit testing, individual units or modules are tested, or modules. Now we're adding that. The components themselves can be tested by the developers. In general, the people who do unit testing are the developers. In general, I say it doesn't have to be, but they are the ones that are usually responsible for testing that the unit that they wrote works. This involves checking the source code by developers. In other words, another developer may check my source code, and this is called code review. So code review is when another programmer looks at my code and makes sure that it does what it's supposed to do. This doesn't necessarily involve the testing team, as I was saying. Unit tests, component tests. Okay. At this level, we test the basic components of the system without testing the interfaces, how it interfaces with other components. We just check whether the software component does what it's supposed to do according to the way the architect designed it, according to the way the designers planned. In the unit test, we will test complicated code. We will test critical code, which is business code, means the main code of the business. In other words, the main thing we're trying to do. We won't check data transfer object, which are classes that only contain members with getter and setter methods. In other words, we don't necessarily test the simplest simplest functions or methods, like get name and set name, because we'll assume that there weren't mistakes there. That was the programmer, either he wrote it, either he knows what he's doing, or he's an idiot. But if he knows what he's doing, he wrote that correctly, and we don't necessarily test that. Right? Why do we even? Right? We generally have those functions because we want to control the way that we set and test, the way we set data, and also we want to make the data private, so we need a get function. But those we generally don't test. Unit tests will include what we call white box testing, which checks the structure and the logic of the code. And this can usually only be done by the person who wrote the code. In other words, you have to be a programmer to do white box testing, because you have to understand the logic of the code, and does it make sense, and does it do what it was supposed to do. And the only person who can do that is the person who, sat down and wrote this code, or at least spent some time going over this code and understanding it and understanding what the requirements were. So this person needs to be a fully trained programmer, not usually the job of a tester. In the code review, you could have another coder checking your code, but sometimes he'll say, well, I'm not going to check the logic. I'm just going to check, if there's obvious errors, or if the style is not good. But usually the programmer himself is responsible to do white box testing. We call it white box because instead of it being a black box where you don't see what's going on inside, here it's white in the sense that maybe you could call it, maybe a better name would be a clear box. You're looking inside the lines of the code and you're seeing, does it make sense? Okay, functional testing. Does the unit do what it's supposed to do? Here we are not necessarily checking how it does it, but just does it do it? Just checking the input and the output, do we get what we were supposed to get? Non-functional tests, how it does it. Does it do it well or not? Now, this functional testing, does it do its function? Non-functional testing is, okay, it does it, but it takes a long time. Or we could do robustness testing, which is that if we give it faulty data, will it crash? Negative testing, to verify the system's resilience for edge cases with invalid input. So here we're going to give it negative testing in the sense that we give it bad information, and or edgy information that's at the edge of the possibilities, and therefore could possibly could be a borderline case that the programmer didn't solve. So we give it like all kinds of tests like that. Of course, to determine what is an edge case, you really have to know what the program is and what the logic is. So that's kind of like white box testing. Fine. But this other one, but functional testing is kind of distinguished. Sometimes we could call it black box testing. We're just testing the input versus the whether the input gave us the output we desired. Okay, coding unit test. This test is the most familiar among computer scientists. So we're still talking about unit tests because it's close to the developer. In other words, the developer himself does it. A method is the smallest programming unit in any programming language. Fine. If we take a class, we test each of the class methods because a method is a significant piece of code. So we will test all the methods except, like we said, for the data transfer objects. The rules by which a method should be checked. Well, we should check edge cases. We should check the simple case, which means the most standard case, not the edge case, but the standard. If we call the first one edge cases, we could call this maybe the middle cases, the cases that are just normal, not at the edge of the possible parameter range. Avoid over-testing the method. Don't test the same thing twice. Notice you don't need to. If it works, if it does 7 times 5 correctly, you don't have to do 7 times 8. It's probably going to also work, unless that's somehow an edge case. In the following 3 examples, we demonstrate how to code a test for a method of a specific unit. So here's an example. Example 1. Given a method divide, whose functional prototype is, okay, so it returns a double, it takes 2 doubles, and obviously it's going to divide them, numerator and denominator, and the method takes 2 doubles and returns the result. The first rule is check the edge case of the method. For example, the first edge case of the method is dividing a positive number by 0. If you divide by 0, well, that's a big no-no. For example, so that's like an edge case. It's a case that it's not the standard normal case. The standard normal case is 7 divided by 4. For example, divide the number 10 by 0. The expected result is what we call plus infinity. In other words, it's an error, but infinity, because 0 goes into 10 an infinite number of times. The second edge case of the divide method is dividing a negative number by 0. So this would be the same thing. You could take 10, you could take negative 10 by 0, and the expected result is minus infinity. Well, okay, all well and good. Those are our tests that we'd run actually on the thing. So here is where we would actually write a test. And what are they? First we call the function and we give it 10 and 0. And we assert equals. We assert that the result that we got, which is positive infinity, posinf, is equal to double, well, that's the type, positive infinity. If we got back positive infinity, then we're okay. And what is this 0.1? That's like the margin of error. If it's close to negative infinity, but it's off by 0.1, then we'll accept it as correct. I mean, in this case, I don't know how you can be off by what it means even being off from positive infinity by 0.1. But theoretically, if it gave me a slightly wrong number, that's acceptable. I can determine the range here. I could put 0 here, in which case it has to be exact. And then we'll do the negative, and we'll divide by 0. And we'll also check that it's a negative infinity. These are obviously defines, these negative infinities, positive infinities. They're defined in the language. So however that's represented in the language, we'll be checking that this result is the same. So here we've written a test. You see, it's actually, we don't just test it by by typing in the number and then seeing what the result we get. We actually run a function that we can just run it and see if we get back true. Wait, I lost the place. There. If the value of the positive infinity variable, which is the result received, is equal to positive infinity, with an error of 0.1, then it passed the test. Otherwise, an error will be reported. Okay, fair enough. The second rule is check the simple case. So we can't just check the edge case, we got to check a regular case. So take 10 and divide it by 2. And the answer should be pos. Pos should be what? 5. So we check assert equals 5 and pos. And again with a precision of 0.1. And if this comes back true, that if this does not fail, asserting means that it'll fail if it doesn't succeed. So if it doesn't fail, then we know it worked. A second simple case of the division function is dividing negative 10 by 2, and we should get negative 5. So we could write that here also, where we write here negative 5 and we write here negative 10. A third simple case. When dividing 10 by 3, we should get 3.33 with a precision of 0.1. Therefore, the simple test method performs 3 tests. So we're going to do, in the simple case, as the first one, we didn't call it simple case. We called it test division with infinity. Now we're going to test, simple. And we have 3. 10 divided by 2, negative 10 divided by 2, and a simple case, and another case, in other words, 10 divided by 2 is going to give us a whole number. But, so why is it different from 10 divided by 3? Because it gives us a fractional number. So we'll test this also. So that pretty much covers it. I mean, can you think of any more cases that we didn't test? Well, he says, no, there is nothing to add to this test we have performed. We've done the edge case, we've done the simple case. The reliability of the code will not increase even if we add more cases of dividing numbers. As we're going to start dividing, 11 by 17, and you could divide all kinds of numbers. We're not going to do every single simple case, because it will not help and will not add anything. We use in this example the JUnit, which is a testing methodology. But can you think of any test that we should have done also? Even though we said here there's nothing left to test, can you think of any tests that are missing? I'll give you a minute, a second. Well, I could think of some things. In reality, there are other edge cases we should have tested. Check where the number is positive, but the divisor is negative. We checked always that the numerator is negative. We never checked that the denominator or the divisor is negative. Or check where both numbers are negative. Now you might say this is not any possibility that those would not work where the other ones did work, but that's not true. There are ways of writing, if you do division by subtraction, by running subtraction in a loop, your counter may be affected by which of the numbers is negative. So depending on how division was done, these would also be edge cases. And that's where we got to the point we said before that this is white box testing. In other words, in order to determine that in actuality there are more there are more edge cases, I have to know something about how the function was implemented. If it was done through a loop of subtracting, and that's how it did division, then there would be more edge cases. But if we call a hardware command of divide, then maybe those aren't worth testing. So these edge cases are depending on how the function was written. Therefore, this requires knowledge of the implementation and is best done by the programmer himself or herself. This is what we call white box testing, where you know something about the program, and only then can you determine the edge cases. Here's another example, sort. In this example, it is more complex than the previous one. It's not just dividing, we're sorting. And the prototype is you give it an array and it sorts the array, an integer array. The method accepts an array of unsorted integers and returns the same sorted array. Question, can the rules we saw in example 1, in the first example, help us to check the code for sort? Not really. There's no place here to use the rules of example 1 because we don't know what the edge cases are. In other words, was there an edge case when maybe it's an edge case with an empty array, but really we'd have to know what the, we don't, it's a complicated program maybe this sort, and we don't, unless we were, if we would have written it ourselves, maybe we would know what the edge cases are. But if we didn't write it ourselves, then we don't know what the edge cases are. And we don't know what the simple cases are. So we will do what's called black box testing. And in this case, we say like this. We have new rules that we must follow. Well, one is steps to follow to test the sort method. First of all, we create what's called an oracle, which we'll see what that is. We'll use an automatic generator to test it with lots of cases. And we actually will perform the test several times. Now, as the previous one, we just created 6, test cases, ran them, and we're done. Here, we're going to create one test case, but run it many times. An oracle, so what is an oracle? An oracle is a method whose job is to check that the sort method, or that any algorithm, sorted the array it received. So, for example, let's see, to understand this, we'll have to see an example. So we're writing the oracle. The oracle is a method that will determine if the array is indeed sorted. Here's an example of an oracle. So it returns true or false, it's Boolean, and it's called isSorted, and we check, is the array sorted? And we take the array by its length, and we run through it, and if the element that we're on is greater than the next element, I guess it's sorted with a descending order, then return false. No, so it should be in ascending order. If we found one that was in descending order, then return false. It's not sorted. So here, first of all, we're assuming that the sort is ascending order, and we're checking for non-compliance here. Here, if the element we're on is actually greater than the following element, then it's not ascending. So return false. As soon as we find one, this function will end. If we went through all the numbers and never found a single one where the following number was smaller, then it is sorted. By the way, this would work for an array of length whose is 1, because it would never run at all and would return true. What about a length of 0? Also would return true. Okay, so the isSorted program is an oracle, because by looping over the array cells and verifying that each cell is smaller than the next cell, it determines if the method produced an accurate result. In other words, it's an oracle in the sense that it tells me whether the result that I got is the desired result. Now I ask, that's actually the original slide, and I ask, is this really a sufficient test of the function sort? Is this sufficient in your opinion? Is there something missing from our test? Assuming that the array is supposed to be ascending, is there something missing? So I propose yes. In truth, this oracle is not sufficient because it doesn't check that the list of numbers didn't get altered. We need to check that all the numbers in the original array are in the sorted array. Maybe the sorted array, the unsorted array had the numbers 1, 3, and 2. And the final result is an array which is 4, 5, and 6. So it's true that it's sorted, but it's not the same array that we had before. It's totally different numbers. Also, we should check that no new numbers. So first of all, I said, is it missing a number? Maybe all of a sudden it's missing a number. It's got one less, or maybe it's got one more. This could have happened because, the first case would be less because maybe we stopped too early. As we were sorting, we didn't go all the way to the end, or it could be that we went beyond the end and we got extra numbers into our array. and I think this problem happened because the definition of the program, the writer of the program, or let's say the writer of the test, didn't really understand the requirements properly. The requirements should have been, I don't know what they were, we weren't given what the requirements were. They should have been that the function shall sort the array numerically and produce an array containing, it should be, the self-same numbers. And produce an array with those exact same numbers, the same amount and the same actual individual numbers. We should also another point is we could also test for invalid inputs. What if the array is floats or letters? In any case, if this requirement is that the self-same and produce an array containing the same numbers. The lesson we can learn from this: writing the functional requirements requires knowledge, skill, and careful thinking. Whoever wrote the functional requirement should have written it something like this, and not just write it, shall sort the array in ascending order. It should be shall sort the array in ascending order without removing or adding any new numbers. And it should be done by an experienced programmer. If the functional requirements are well done, then the testing will be able to be more accurate, because the tester will look at that and notice that it says also check for missing numbers. What happened in our case is that both the person who wrote the functional requirement and the person who wrote the test assumed, well, of course all the numbers in the array should not change. But since this was assumed, it was never written down and therefore was never tested. Everything that you assume should be written down so the tester will know how to test. Okay, assuming that we've written this function and it's to our liking, it's the way it should be, we now have to use it. So we're going to use a random generator to create an array with a lot of numbers in it. So quick reminder of the method random. If I do math random, I'm going to get a number between 0 and 1. And if I multiply it by 10, then I'll get a number between 10 and 0. And if I cast it to an int, then I'll get just a whole number between 0 and 10, up to 9. Okay, and I could do it any way I wanted. I could multiply it by 10, I could multiply it by 100. What is a random number generator? It's a function to generate numbers and store them. Well, in our case, we're going to store them in a one-dimensional array. Here is our example. We use this random function. We get, first of all, the size of the array we determine. It's up to size 10, or up to size 9, actually. So here's our size. We're going to make an array, let's say, of whatever random number we get. Then we're going to say, we've got our size, so create, let's say our size is 9, so we're going to create 9 numbers. So we run our loop 9 times, and we say run random again, and now this time multiply by 100, and we're going to get a value from 0 to 99. And we're going to take that value and put it in the first place in the array, and the second place in the array, etc. So we're going to fill up our array with up to 9 numbers. And it's a random number. It produces a random array of integers. Not only is the array size random, but the values in the array are random. Of course, they're within a range. We might get an array like this: 87, 53, 5. Fine. Now we're going to perform the test several times. So we're going to do like this. We have our function here. Here's our function, generate array, and it creates a whole array. So we're going to say like this. First of all, generate an array, and that'll be called input. And then we'll run sort of the array and give it input. Now the result should be returned by the function, and we're going to run the function is sorted. Is it sorted? Which we already wrote. And we got to assert that that's true. And all of this is for one array. But we're going to run it in an array 10 times or 100 times, and whatever the loop's value is. In this case, 10 times. So we're going to 10 times create 10 different arrays of varying sizes with varying contents. And we're going to assert that they're true. which means that if any one of them is not sorted using this oracle, then we know that our function sort, which is what we're testing really, didn't work properly. That's the idea. Of course, you could say, well, we need to test generate array that it works. That's probably true also, but assuming that that the error, I mean, even if there is an error there, it shouldn't cause all of a sudden sort, which had an error, to all of a sudden start working correctly. It would be very unlikely. So if there's any error in this, we assume that there's an error in sort and we look for it. If we can't find it, we might check generate. We might check generate array, or this function is sorted. But presumably their errors are not compatible, and therefore if we get an error, there's an error, and it's probably in sort. If we don't get any errors, then we assume everything works. So this is black box testing, because we're not interested in what the edge cases are. We're just testing lots and lots of cases. We wrote 3 methods: is sorted, generate array, and test sort. All 3 methods constitute one test, and its coding is longer, therefore. We demonstrate how to perform a unit test with the sort method using the following rules. We used the oracle, we used an automatic generator, and we ran the function 10 times. Remarks: the more times we test the sort method, 50 or 100 times, the more confidence we have that the sort function works. Now, as we can never really be sure that it works because we didn't know what edge cases there might have been. But we tested it a lot of times and with a lot of different, arrays. So we have a higher confidence. We can only say it's a higher confidence that it works, but we can't be sure. This is a kind of brute force testing. We rely on brute force when we don't know the inner operations of the method and therefore treat this method as a black box. Okay. Let's look at unit testing example 3. This example will demonstrate how to perform a unit test on an entire object. We have a class called stack example, that implements a simple stack. And the implementation of the class is that there is a max size, there's the current size of the stack, and there's how many elements are in the stack. There is the stack, which is an array of objects, is the stack itself. We have a stack X, which is the constructor for the stack. We have a put function, which puts an element in the stack, a pop function, which removes, and a size, which tells us the current size. Okay. To check the entire object, we have 2 new steps. Testing each of the class's methods, test for side effects. So explain the first step. In the class named stack example, there are 2 methods, push and pop. There's 2 essential methods. That's exactly what we said before. We don't check just something like get size or the constructor function. If the constructor function doesn't work, then the whole thing's not going to work. We only check the functions that are essential or not essential, that are the main working of the thing. What makes a stack is that it has a put and a pop function. So we have to write 2 tests, one for put, and one for pop. I could call it push and pop. Okay, first test. Write a check size. The check size method that checks the size and is updated when put method is invoked. In other words, we would hope that when we put a new object into the stack, the size of the stack increases. Not the max size, but the actual size in the sense the number of elements in the stack. So the point of the test is to add more and more elements to the stack beyond the limit and check that those objects which are beyond the limit have not entered the stack. I mean, we could have also checked that when we put in 1, it tells us 1, and put in 2, it tells us 2. Of course, that doesn't actually guarantee that they're actually in the stack. We would only, right, it would just tell us that we can't put how many we've put in, but it wouldn't necessarily prove that we got the actual data that we wanted. So let's just follow in the order of the slides here. So check the size. So we say it like this. We have our max size as, let's say, 10. And then we put in 10 elements. But we didn't do it till 10. We did max size plus 5 here. So what we're saying is put in more than you're allowed and just keep putting them in. And now, after we ran this loop, we've put in, let's say, 15 elements, but only 10 got in. Now we assert that the stack size is equal to max size, which is 10. In other words, those extra ones didn't get put in, because you can't put into a stack larger than its max size. That's a pretty basic test. The second test is writing a null for empty method that tests the pop method. We're checking here that if we empty the stack and try to remove an element from the stack, it will eventually return null if we keep going. So here we go and we say, according to the current size of the, not the max size, but the current size, we're going to remove elements. We're going to do a loop, and we're going to remove every single element according to whatever size you say there is. Whatever the size is, we're going to, of course, when I pop, the size will get smaller. The truth is, this I++, now that I think about it, is an unnecessary. I could have just done while size, or while I, and I don't need the I++, while I equals 1. As long as the size is less than 1, because when I do pop, the size should automatically go down. So eventually, even though the I never changes, it would be sufficient to, so basically this I++ is unnecessary. But that's a side point. This will work. Actually, this will not work. I think this is wrong. I should tell the person who wrote this slide that this is wrong. Yeah, this is wrong, in my opinion. This is wrong because pop, depending on how pop works, pop should remove the size of the stack. Remove something. Object, anyway, object. Now we've removed everything and we do another pop. It should be, this object should be null, and we assert null. Is this null? If it fails, if it's not null, this function will fail and we'll know that our test failed. Of course we didn't. Okay. So explanation. The most complicated thing is to check that the many combinations that exist between different methods. And the put and pop method, in the put and pop method, we try to add one and then remove it and check that we are talking about the same one that we put in. So here is a good example. Put and pop. So we put in the actual value 1, and then we assert that when we do a pop, we get the one that we put in. That's actually really where we should have started, just to make sure that the 1 is that the numbers that we put in are the numbers that we get out. And as it's one thing to tell us that it's full, it's not full, but that wasn't the goal of the stack, to just be full, to tell us when it's full, and to not put in more things and tell us when it's empty, but to actually get the numbers that we put in. So here we put in a number. Now if we put in 1 and get back 1, that's also not really enough of a test. We should put in at least, because that doesn't prove that it's not a FIFO. We should put in, it could be first in, first out, and not a stack. So we should really put in 3 numbers and then pop them and see that we got back those 3 numbers in reverse order, or in reverse order. We'll stop here and continue with integration tests. Okay, we are continuing the lecture on software testing, and we finished unit testing. Now we're going to talk about integration testing. What are we checking in integration testing? The purpose of the test, that there are no bugs as a result of assembling the components together. Each component works by itself, but do they work together? If we have thoroughly tested every component in the application, we know that there'll be no bugs or anomalies in the units. But what about their interactions? Integration testing, individual modules are bundled together and tested by developers. The goal is to determine which module sets work together as expected once they are integrated. There's 2 choices. Either you put all the components together and see if the system works, or you can try bundling subsets, like 2 or 3 components together, see if they work. Then a different set of components, and if and then you could, by doing that, you could isolate which component combinations are causing trouble. Because if you just prove that the whole system doesn't, if you put them all together and prove the whole system doesn't, and you find that the whole system doesn't work, your job isn't done. You got to figure out which interaction is causing the problem. So you may group them in different ways. Integration testing. We check complicated interactions, critical components, complex interfaces. Interfaces is very similar to interactions. There are two main ways to approach integration testing. Component integration. Integration between parts of the system, such as graphics cards, I don't know if that's CAD, computer aided design, or card. I think graphics card drivers and the operating system. System integration, integration between our system and systems outside the system. In other words, there's two parts of integration. There's integration, internal integration, with the different parts and the operating system, let's say. And the other is integration with external systems, like, it has to work with the Internal Revenue Service or something. Those are two different aspects of integration. What are some strategies? You could do incremental testing. Once an interface is ready for testing, you test it independent of other interfaces. This way you can easily isolate faults and start testing early. In other words, you could basically integrate the components one by one as they become available. The other idea is wait for all the components to be ready, and that's called Big Bang testing. And then you do everything at once. Such testing is more dangerous because if we discover faults, it might be difficult to locate the cause of the problem. Well, that's why I said before you could group you could go back and unconnect things and then see if the components work one by one. Obviously, that's going to be difficult too. System testing. When an entire system is ready and the integration tests of all the subsystems, no, we finished integration testing. Now we're talking about system testing. And the internal components have been completed. We perform tests to answer the question, does the system meet the requirements? This test is based on the requirements document and the threshold conditions for accepting the system. In other words, we maybe don't have to meet all the requirements, but there's some threshold of requirements that we have to meet. Does the system meet them? Here we can do black box testing, check that the results against the requirements. Now, we're not going to do white box testing here because we don't know the internal workings of the whole system. No one person understands it all, perhaps, and cannot possibly, think of what edge cases there are for the system as a system. So therefore, we'll just do black box testing. We'll put in inputs, and we'll see if we get the output that the requirements document told us we should get. The tester looks at the application as if they were a user, and they check for noncompliance with customer user requirements. In other words, can I get the results that the user wants to get from the system? System testing. In system testing, we will check the following. The simple cases, the way the system is usually used. Once there is a defect in a simple case, your application is done for because no one will want to use it. You got to get the simple cases working. Now you have also, we don't really know what the edge cases are, like I said. But we also can check what's called monkey testing, which is unexpected scenarios. It's a complicated test to write because it requires sort of randomization. But the reason why it's called a monkey testing is it's because we're essentially giving our program to a monkey and let him click any and all keys and check that the program doesn't crash. In other words, we're just seeing, is there some combination of presses that will, some unusual, maybe illogical combination of key presses that will ruin our system. There are tools that allow for the automation of these tests. Obviously, you're going to want to keep track of what the test was that crashed. So you can't do it, you can do it randomly, but it has to be recorded. Okay, acceptance. So the fourth test that we have now is the acceptance test. Right? We had unit tests, we had unit tests, and then we had integration tests, then system tests, and now we're talking about acceptance tests. Test is a test by the final customer to ensure that they have indeed received the system they expect and are satisfied with how it performs. User acceptance test is, like I said, by the users. Operational acceptance testing is performed by the system administrator, focusing on aspects of backup, recovery, data restoration, the degree of vulnerability of the system. In other words, can it be hacked? So those are operational acceptance. In other words, it's fine that the user says it works, but maybe it's easily hacked, or maybe it's impossible to do backup, or if it crashes, it's impossible to recover lost data. Then there's contractual testing. There's a contract between the customer and the producer of the software. Does it meet that requirement? And then there's compliance testing, which means compliance in the sense, does it comply to regulations and legislations of the countries that use it? I don't know why FDA, Federal Department of Agriculture, I'm not sure, maybe. But anyway, the point is different governmental organizations may have rules about, let's say, data security. Can a user get back his data? Who owns it? Does the company own it? All these are compliance testings. There's another term you may have heard at some point, alpha testing, or you really probably have heard of beta testing. So what are they? Alpha testing is testing by the software developing company itself, mainly for off-the-shelf products. In other words, there's no client, but we decided that we're going to make this product. So we want to assess, is it doing its job before we start selling it? Beta testing is that we basically are ready to give it to the public, but we're not sure. So we give it to a small subset of the potential clients or customers, and we get feedback from them regarding the product. Again, this is mainly for off-the-shelf software. In other words, not contracted software. So a beta tester is simply a user who uses something before it's officially ready, and he's supposed to report back his opinions and what he found fault with. So that's human testing. Test writing process, the classic method. So we start from the right over here. You do some kind of planning, you do analysis and design of the test we're talking about. Implementation, you evaluate, and you determine whether it passed the test or didn't pass the test, and then you close the whole project of testing it. There's a term here that's mentioned, sanity testing. I think we're going to talk about that later, but here it says, under implementation and execution, you do what's called sanity testing, which means sanity testing sounds scary because something insane. What we're talking about is that the program basically works in the normal case. That's what sanity testing. Am I getting basically sane results? In other words, if I'm calculating the weight of, I don't know, the gravitational pull of a faraway object, is it within the range of possibilities? Am I getting a result that makes sense? Or am I getting, is the system working the way it's supposed to in general, without dealing with edge cases? This is a method from develop. This is the stages as defined by the International Testing Organization. Okay. So what are these things? These planning, and we have a long list. So planning and control is writing an STP document, a software test plan. That's what STP stands for, software test plan. Defined according to the IEEE. And it should include, so we have to first of all have a plan. What is our plan to test? What are the goals? What are determining the test goals and actions to achieve them? Determining the content of the test. Identifying system boundaries. In other words, what the system will do and what it won't do. What is our testing approach? Defining it. What are our policies and our strategies? What resources will we use? What's the schedule? When will we do it? And entry and exit criteria for test levels. When do we go from one test level to the next? Like we said, what the test levels are: unit testing, component testing, system testing, acceptance testing. Control, comparing progress in various tests against planning, status reports, and deviation from the original plan on what is being done to achieve the project goals. In other words, there may be changes in our testing desires as the project changes. Updating the planning according to the control results and defining the use of indicators and reports. All that is planning. Analysis and design is the next stage. We plan the test cases using all the requirements documents. So now we actually look at the requirements documents that the programmers use to program what they want to program, and we plan the tests. Examining whether the functional requirements can be tested. Can we make a test of this at all, or is it impossible? Or what kind of test can we do? Can we do a white box or black box? Prioritize the tests. Which tests are more important, or which ones will we do first? Identifying the test data. The data that must be prepared in advance for the test running phase. In other words, maybe we have to feed certain data into the system in order to test it. What is that data? The third step is implementation, which is actually writing the test cases. Each test case can include what are the prerequisites for the tests. In other words, what data do we have to have? What value should be entered into the test? What are the actual values that the data should have? What is the expected result we should get? What should we get for each data? For each piece of data that we put in, what should we get as a result? Preparing test data necessary to run the test scripts. So we got to create a file of all the data so that the test scripts can, let's say, read from that file and then run the test according to that data. Planning the test, or maybe it's not a file, maybe it's a database. That's all part of the planning that we already did, and now we just have to actually put the data there. Planning the test environment, infrastructure, and tools for running the tests, how they will be performed manually or automatically, usually automatically. Creating test suites. A test suite is a set of tests to test a particular unit or component or a set of components. A collection of test scripts arranged in a specific execution order. The system state at the end of one script serves a prerequisite for running the next script. In other words, it has to pass the first suite in order to run the second test. First in the suite, there's several tests. It has to pass them in a certain order. And perhaps the result of one is the actual feeding in data for the next. At this stage, it is necessary to verify whether all requirements have been covered by the test. Did we miss anything? Did we have a test for all the requirements that are in the requirement document? And is it also necessary to ensure that the environments are suitable and prepared for testing? Maybe we need a certain operating system, we need certain databases to be available, we need an environment. And that the test personnel are available and ready. Have we hired people to do this? In addition, check if necessary licenses, drivers, etc. are available. Okay. Now we execute the tests, right? The tests are all ready. We planned them. We've created the data for them. We've created the actual tests. Now we have to run them. There's something called smoke tests. Before running the tests, smoke tests are performed in which a script is run for the main functionality in the system to ensure that the basic level is ready and you can begin to delve deeper into the tests themselves. In other words, smoke test is kind of like a preliminary test. I think we called it, what did we call it before? We had another name for it. It's a good review. We called it the simples case. It should be simple. Simple case. Simple cases should be. But here we're calling it a smoke test. We didn't really give it a name. So smoke test. Before running the tests, we have to make sure the basic functionality is running. Then running the tests. Run the written test scripts. You can run automated tests. Document the results. Did it fail? Did it pass? Did you not finish the test? Did you not run it at all? You do that on each line of the test case. Compare the results. Look at the results. See how well you did. Evaluating the exit criteria and reporting. We have an STR, summary test report. After we have finished performing all the tests, we will create a summary report of the performance of the tests. In addition to the test results, the report includes analysis of information and dimensions differences between the original plan and the actual execution of the test, assessment of open, false, existing risks, and the degree of security in the system. Now, did we actually complete all of our tests? Did we do different tests? Did we invent new tests along the way? Are there still problems that we haven't yet fixed? Open faults, in other words, bugs that have not been fixed. What risks are there? How secure is the system? All those are opinions, kind of. Closure, final checks before finishing the test. Have all the tests deliverables, in other words, the tests that we wanted to do, been delivered? Have we finished them? Have the open bugs that were fixed been closed? In other words, if we fix the bug, we should close it now. Or being moved to the next version, or are they being moved to the next version by an agreed decision? In other words, maybe we decided we're not going to fix this bug until the next version. Store the entire test environment scripts. Now, we're going to keep our whole test environment, which is our databases with all the information and all our scripts that we were on, all that data. We're going to keep it for future use. Transfer the test environment, the testware, and put it in some place to store for maintenance, or analyze and draw conclusions from the testing process in the project for future improvement. In other words, we have to decide, was our testing process a good process? Did we do our testing well? We have to come up with an opinion about that. After we've, that's in addition to deciding whether the project was good, was our testing good? Now, that's all the classic steps in testing, with lots of stages and documents and planning. Now, there's something called rapid software testing, the FAST method. And this is James Bach, his theory. He worked at Apple in the 80s and the 90s, and he has some theories about testing. I think he wrote a book. His theories were formulated over the years, and in 2001, he published his model, RST, Rapid Software Testing. He is an opponent of traditional testing, traditional theoretical testing. As far as he's concerned, all the fuss about writing tests is a waste of time. In his model, he talks about how to become better testers under pressure and suggests 5 main topics. In other words, this is all like as though you have, what we've done up till now is as though you have an infinite amount of time and you're going to plan your tests very carefully. But what if you have pressure and in the real world, you want to get things out the door, you want to finish, and you want to sell it and make money. So you can't just have all the time in the world. So he says, stop doing things that don't help, like writing tests. Consider risk management. What is our risks and which risks are bigger risks, and only deal with those. Use tools to speed up the testing process. How to explain tests and their value to managers. We have to think about that. We can't just have a test and the manager may just say, okay, whatever that test, maybe it's a stupid test. Tell them the importance of the test, or which tests are important and which ones are not. Always improve your ability to do all the things from the previous sections. So in other words, stop doing things that don't help. So only do the useful things. But it sort of contradicts, because it says writing tests is something you're going to stop doing, but then use tools to speed up the testing process. Well, you're going to have to write a test to use a tool. He's going to have to run something. Anyway, you'd have to read the book really to understand it, but his basic idea is you don't need to do so much planning. Write some tests, run the tests, make sure that the managers understand the meaning of the tests, and that's all. Okay. So then there's something called TDD, test-driven development, which you may have seen if you learned about extreme programming. And the idea of test-driven development is that you write the tests ahead of time, then you write the application, then you perform the tests on the code. If there's a bug, you fix the bug, and you return to writing a new test. Or you turn to, actually, it should really be, if there's a bug, fix the bug, and then return to 3. After 4 should include return to 3. And then if there's no bug, then write a new test. So you're always writing, so you start off by writing the test. And that, if you think about it, we did. We wrote some tests earlier in the previous lecture. We showed you some unit testing where we tested the push and the pop, and we could write those tests before we actually write the function. And then we know what we have to accomplish in our program. First of all, it says the advantage of the approach is that it's popular. Well, that doesn't really tell me why it's popular. It doesn't tell me really what the advantage is. Maybe it's advantageous because other people are using it, so therefore you can talk about it. But the advantage, I would say, what is the advantage of a tester? Is that you won't forget to write a test. I think that's one advantage. A lot of times you'll write the thing, you'll write the program, and you'll see that it works, you won't bother to test it. And you'll never write a test. So this way, since you start with writing a test, you're not going to forget to do it. Secondly, by writing the tests, you actually define clearly what the program is supposed to do before you've written it. You could show your test to another programmer, and if he says, no, you didn't test the right thing, then you realize you didn't understand what the problem was. Instead of wasting a lot of time writing a program where you didn't understand the problem, here you write the test, and now somebody can give you feedback on your test and tell you, does this test demonstrate that you know what your program is supposed to do? So that, I think, is the real advantages, but it's not written here. Disadvantage of the approach. It's not easy to actually do this. In other words, it's not easy. People are lazy. People don't want to actually write tests. They just want to start writing the program. Okay. What is a software tester? In the past, it was assumed that the tester's role was to carry out the test and verify their results. The testing organization expands the scope and defines the additional activities within its area of responsibility. Planning. In other words, we thought he was just to carry out the tests and check that they were right. Now we say no, he actually is not just going to carry out the tests, he's going to plan the tests, analyze the test design. Think about how he's going to be in charge of designing the tests and creating them. And then he's going to write the tests as an automation, implementing them and running them, and then reporting the results. I mean, it doesn't have to be automation, but usually. Determining the quality of the software being tested. And he'll actually say whether it's good or bad. Says in the past, it was just simple. Somebody else wrote the test, and I just run them and see if it works. In most companies in the past, the person who would write the test was the software developer himself. And then the tester would go and test. The tester's job would be to test it. He wouldn't write it. Today, in many cases, we have become smarter. The problem is defined as the authorship bias or author bias, which means that if the developer developed the software, he's the author of the software, he won't be objective about what needs to be tested in it. And as he sees the problem from a certain vantage point, and he has certain blind spots that everybody has. And he'll write his tests, those tests that are have the same blind spots that his writing had. So if he really did forget about something, he'll probably forget about it in the test. The chances that his test will include something that he forgot about is unlikely, because that's his blind spot. So it's better to have somebody else write the tests. And therefore, someone objective is needed. The right person would, of course, be a tester. Now, you could say, well, let another programmer write it, but then you're taking him away from valuable programming. So we have another class of workers who are testers who are supposed to think about the software from an outside perspective. What are the duties of the tester? Evaluating products such as requirements documents. He's supposed to look at the requirements documents, the design, and code writing. He's going to look at everything. Ensure that all the customer's requirements are met. Make sure that the programs are actually fulfilling what the requirement documents say they should do. Confirm that the tests are complete and that the software is working as expected. So he has to make sure not only to run the test, he's got to give it the stamp of approval. Say the software worked, it passed the test, or it didn't pass the test. He's got to, and by doing this, he'll build trust in the system. If he says his word should be gold, if he says it works, or she says that the software passed the test, then now we can trust the system. Obviously, he's tried to prevent defects in the system. finding defects of failure in the system, finding the failures, providing stakeholders, people with an interest in the company, with an honest assessment of the software and its quality. He's supposed to say whether it's good or bad. How good is it? How unique is it? Reducing the level of risk associated with using poor software. If he can create good software, then we're going to have not so much risks like financial loss by having used poor software or deaths or lawsuits. Ensuring that the software meets regulatory, he's also going to make sure that the software meets legal requirements of the state or the country that we're in. Okay, we continue now with the types of tests. There are functional tests. That's pretty much what we've discussed up to now, because we're seeing if it functions properly. There's also non-functional testing. There's also testing on the level of the code, and testing after there have been changes made in the program. Okay, so first of all, non-functional testing. We're going to test for things like efficiency, where we want to check the load and performance of the system when there's a lot of data, or how fast will the system respond when there's a lot of users if it's a multi-user system. So there are several types of load tests. We can load testing the server-side response in a server-client system if we have that expects many users at the same time. So we have, let's say, a server-client situation. We can see how the server responds when it's heavily loaded, how quickly it responds. Then there's stress testing. The system response time under load and finding the system's limits. How smoothly can the system work before it crashes, in which we were testing system stability, recovery, and response times according to the number of simultaneous users, the number of processes occurring simultaneously. So that's both load testing and stress testing are pretty much the same thing. I don't see much difference here. They're both dealing with many users at the same time. And we're both interested in seeing how the server responds, how quickly it responds. Volume testing, system response time when the database is full, or 80% or higher, measures both by simultaneous user load and process load. So if the database is full, maybe it's slower to find the data that we're looking for. So how does the volume of data affect response time? Usability these are all things that are not the functionality. The system works. We're just seeing how well it works under stressful circumstances. Usability, is the system easy to operate, user-friendly? Does it accord to the GUI, to the graphical user interface specifications that we have made? Does the GUI affect the required results? In other words, when we press on the GUI, does it actually bring about the results that we wanted it to? Portability testing. Can we use our system on with different browsers, with different operating systems, and with different kinds of databases? And then there's maintainability testing. If we want to change things, is it easy to change? Can it be changed? This obviously has to be done by the development team because they understand the inner workings. Those are all non-functional because they all deal with things that are beyond the question of whether it functions. There's also more. Reliability testing. Testing the reliability of the system into business activities according to requirements over a defined long period of time. And does it continue working for 72 hours? Or does it, after a certain number of hours, does the system crash? Recoverability testing. If there's a power outage, can we get back? Do we get lost data? Do we lose data, or can we somehow maintain a copy of data, a temporary copy to be able to reinstate the processes that we're in the middle of doing? Security testing. Is it hacker-proof or hacker-resistant? Documentation testing. Are the manuals up to date and accurate? Interoperability testing. Does the system interface testing? Is it system interfacing testing? In other words, can we use this system with other systems? Does the API work? There's also structural testing, testing that depends on the structure of the code. Here we examine the code and its structures, such as reading tags on a website or examining Java code, mainly at the unit testing level, but also on other level. Well, for example, code coverage, the degree to which the source code of a program is executed when a particular test is run. In other words, maybe there's some kind of structural problem in the code and we never got to a certain case. So did we cover all the code? Did our tests cause all the code in the program to be run? Or maybe we did a test, but some of the parts of the code never got run because they were for errors or things like that. There's such a thing as white box testing. We talked about testing a system component based on the internal structure of the code. The component should be visible to the tester, which means he should be able to see, he should understand the inner workings of it. And the tester should, of course, be familiar with the development language. He has to understand the programming language. You have to know Java if it's written in Java. There's also change-dependent tests. How the software will behave after changes such as upgrade, bugs, fixes, etc. Confirmation retesting. Check to make sure that the repair has actually resolved the problem it was supposed to resolve. Regression testing. Rerun functional and non-functional tests. So all these functional and non-functional tests, we're going to rerun them to ensure that the previously developed and tested software still performs as expected after a change. If not, that would be called a regression. In other words, we've added something, but it's actually made us go backwards in time. We've actually lost some functionality. New faults may be discovered. So we're going to have to retest things that have already been tested every time we add something. Obviously, we don't want to do this manually. So therefore, we're going to have test scripts. I mean, if you think about it, that's why when you have an agile system or a system that assumes there will be updates, we must have automated testing because we have to test the whole system every time we make a change and every part of the system. So we need to do that automate. We need to do it with scripts and programs, not by manually testing things. In summary, each type of test has a different goal. Therefore, at each level of testing, unit testing, integration testing, system testing, and acceptance testing, those are the 4 levels, we can test for all 4 types. We can test in all 4 types of testing to encompass the object being tested for from all possible directions. In other words, we have to always test all 4 of these aspects. Now we're concluding with some general concepts of software testing. There's such a thing as dynamic versus static testing. We talked about that actually. We said that static testing is where you just check that the code runs. And dynamic is that it performs its mission. Development versus independent testing. Automated versus manual. Sanity versus smoking. And monkey testing. Okay, so dynamic versus static testing. The test is done by running the program in dynamic. In static, you don't run the program, you just compile it. Dynamic testing deals with finding and fixing defects. Static is about preventing defects because if we find a bug in the static level, then obviously it's not going to work when we try running it. Dynamic testing reveals bugs, bottlenecks in the software system. Static testing provides an assessment of the code and documentation. Okay, development testing versus independent testing. Development testing means that the developers themselves, during the development process, try to discover defects to reduce the risks and time and costs of the software development. Because if we can find the risk early on, we can save a lot of time. Then this independent testing is done not by the developers themselves, but by someone who did not develop the system to avoid developer bias or author bias. Often more effective in finding defects. Development testing versus independent testing. An independent test can be performed by independent testers responding to the development team, independent testing team in the organization. Notice it can be internal or external, even if it's independent. It's independent in the sense that it's independent from the team that did the development. It can be from a different organization. It can be outsourced team, test team members outsourced from another organization. Okay. Advantages of independent testing. The examiner sees every flaw from a neutral perspective. The examiner is completely impartial. The examiner sees what was built and not what the developer thought he was trying to do. As he just sees the actual thing. Disadvantage of independent testing. Isolation from the development can sometimes result in outdated documentation. Right, the documentation can reflect what from a certain version, and as the development went on, they changed the way they were doing things, and the documentation was already written. Performing the independent review is usually at the last step and is affected and delayed by early delays in the process. In other words, if I have an independent person doing it, it's probably going to be after the team says they finished. So that means they can't start testing until much later, and that means that slows down the whole process. Developer may feel not responsible for quality because they can say, well, that's not my department. Somebody else is going to test it. Quality assurance independent testing. An independent testing organization is an organization, person, or company that tests products, materials, and software against agreed upon requirements. The testing organization may be affiliated with a government or university, or may be an independent testing laboratory. They are independent because they are not affiliated with the manufacturer or user of the item being tested. There is no commercial bias. These contracted shouldn't be commercial bias, authorized. These contracted testing facilities are sometimes called third-party testing or evaluation facilities. Development testing and independent testing are not intended to replace quality assurance, but only to improve and increase the quality of the system. Smoke test versus sanity tests. So sanity, the long and short of it is that sanity testing is on a unit and smoke testing is on a system. But let's see what's written here. Sanity testing check is done to check the new functionality. Smoke testing is performed to ensure that the crucial functionality of the system is working fine. It's like a basic test of the whole system. Here is a check on a new functionality that has been added or a bug fix that has been done, a particular small thing. Here, if you look at the fourth thing here, sanity check only checks the specific component of the entire system. Smoke testing runs the entire system end to end to check it. Okay, the second point. The point of the test is to rule out certain classes of obviously false results in part of the system, not to catch every possible error. The purpose of the smoke test is to verify the stability of the system, that the system as a system is stable in order to proceed with more rigorous testing later. Basically, is the system working? The third, sanity tests are usually conducted by testers. I'm not sure if that's true. The sanity test can be done by the developer too. The smoke test is usually done by the developers or testers. I don't know what this point is here because I don't think so. I think that smoke test is usually done by testers, but it could be done by developers, but it's usually done by testers. And sanity check is usually done by the developers. Sanity check is like a special health check. Smoke check is like a general health. Okay. Sorry, going the wrong way. And the last slide is monkey tests, is a technique in which a user tests an application or system by providing random inputs and testing behavior or testing whether the application system will crash. It's typically implemented as an automated set of random unit tests. Think of a monkey running amok and entering random values into the system. Will the system respond correctly and cope with this, or will it crash? Okay, that's pretty much everything we have to say about testing on a theoretical level, and we even saw practical examples of unit testing. And good luck, and see you in the next lecture.